This lesson is on representing series with functions, specifically infinite geometric series in what we call a power series. So what do these look like? So let's first by expanding this out. So if we plug in 0 for k, we're going to have 1. If we plug in 1, we're going to have x. Plug in 2, we'll have x squared, and so on. So this is an infinite geometric series. My a1 is 1. My common ratio, the thing we're multiplying to get from term to term there, is x. So we can write an expression for the sum, since we know our sum is a1 over 1 minus r. Plug in our respective values. So a1 is 1 over 1 minus x. So this is the sum, but for only some values. This isn't, if x is 2, then this series is going to keep getting bigger and bigger and bigger. But if this is, say, 1/2, then we're good to go. These are going to get smaller and smaller and smaller. They will be an infinite geometric series that has a sum. So this is only valid when our common ratio, which is x, is between -1 and 1. And this is called the interval of convergence. So let's do another one. We have a -1 here, then we have that same x to the k. So we plug in 0, we're going to get 1 again. When I plug in 1, we're going to have a negative x. When we plug in 2, we'll have a plus x squared. 3 gives me a negative x cubed, and so on. So it's very similar to the first one. My a1 is still 1, but my common ratio this time is -x. So when we plug it into the sum formula, we'll have a1, which is 1, over 1 minus -x, or plus x. Okay, let's solve for our interval of convergence. So -1 is going to be less than -x is going to be less than 1. So I'm going to divide everything by -1, or multiply by -1, which makes this 1, but turns the inequality around. -1 to 1. So really, when I divide, it's going to switch everything around, but then the negative's going to end up back here. So I'll oftentimes just go from this step to this step with the understanding that this happened in between. All right, let's see what this 2 does. Still going to be alternating. First term is still going to be 1. My next one's going to be minus. I'm going to plug in 1, so this is going to be x squared. Plug in a 2 will make this, make this positive, make this x to the 4th. Plug in a 3 will make it negative x to the 6th, and so on. a1 is 1. r is a negative x squared. So the sum is going to be 1 over 1 plus x squared now, because we're minus the r, which is negative. My common ratio is going to be when x squared, negative x squared, is in between -1 and 1, which is really when x is between -1 and 1. So you can do the opposite thing in square root, but you're going to end up with this regardless. Okay, we're going to find all values of x for which the series is convergent, and then find the sum. R here is what we're multiplying to get from step to step here. So my r is going to be e to the -x, because if I multiply e to the -x times e to the -x, we add those exponents to get a -2x, and then add another one to get -3x. Well, when is this between -1 and 1? Well, the graph of e to the -x, okay, it's exponential to k, e to the 0 is 1, and then it's going to go like this. So it's never going to be negative, but it's going to be less than 1 for just this part of the graph. So we're going to say when x is greater than 0, then my common ratio is between -1 and 1. My sum then is going to be a1, which is e to the negative x, over 1 minus e to the negative x. Okay, this one, starting at n is 0, so sine to the 0 is 1. We're going to have plus sine of x plus sine squared x, and so on. So my common ratio is sine of x. So when is sine of x between -1 and 1? Well, sine of x is almost always between -1, except for when it is 1 and -1. So it's going to be 1 at pi over 2. It's going to be -1 at 3 pi over 2, which is pi away. So this is all real values except for pi over 2 and any multiple of pi of that. So pi, 3 pi over 2, 5 pi over 2, and so on. I'll just say all except. Something like that. Alright, our sum is just going to be 1 over 1 minus sine of x. Alright, so new series from an old series using substitution. So we're going to write the first 4 non-zero terms and the general term for the power series given. Okay, so this is my a1 is 1. My common ratio, if this is a1 over 1 minus r, my common ratio is going to be -3x. So we're going to have 1 minus 3x plus 9x squared minus 27x cubed, and so on. The general term, I'm just going to dump into the power series in sigma notation. So I'm going to start with n equals 0 to infinity. We're going to have 1 times -3x to the n. Okay, and then when what's the interval of convergence? That's going to be -1 is less than -3x is less than 1. I'm going to divide by 3, and again this negative is just going to switch everything around. So I'm just going to divide by 3. So my interval of convergence is when x is between -1/3 and 1/3. Alright, this next one, same story. I want to find the a1 and the r, but it has to be a1 over 1 minus r. Okay, I need it in this format. I don't have that. That 2 is being problematic. So I'm going to factor a 2 out, which will leave me with 1 minus 1/2 x. Okay, so I can move this the 2 up to the top, so this would be 1/2 over 1 minus 1/2 x. Now we're in the correct form. So my a1 is 1/2. My r is going to be 1/2 x. And then we can form the series. So of 1/2 plus 1/4 x plus 1/8 x squared. And so on. When I plug it into the sigma, I'm going to start at 0 and go to infinity. And then I'm just going to do a1, which is 1/2 times my common ratio, 1/2 x to the n. So a1 times r to the n is going to be my formula. When is this valid? So our interval of convergence is going to be when -1 is less than 1/2 x is less than 1. So between -2 and 2. These ones here, you could, because this isn't a constant up here, you could pull that out and then just multiply by x. I'm just going to say that's my a1. So I'm just going to say a1 here is x. My common ratio is 2x. So remember, it's 1 minus r, so whatever this is, its opposite. So this would be x plus 2x squared plus 4x cubed is 8x to the fourth. So I'm going to write this as a1, which is x, times 2x to the n. My interval of convergence is between -1/2 and 1/2. Alright, a1 is x squared, r is x squared. This is going to be x squared plus x to the fourth plus x to the sixth plus x to the eighth. So in sigma, there's always multiple ways to write things in sigma notation. This one, if I did my a1 times r to the n, it would be like this. We could also look at this, we're x squared, x to the fourth, x to the sixth. So I could, if I wanted to, write it as when n equals 1 to infinity of x to the 2n. That would give me the same thing. So there's multiple ways, but if we just want to dump it into a1 times r to the n, we're there. Another thing to consider, questions like this would almost always be a multiple choice, so you would just have to match it. Common ratio, -1 is less than x is less than 1 squared when x is between -1 and 1. Okay, this one. This is equivalent to this if I used partial fractions to simplify it. So what is this? So I'm going to expand this one out. So this one, my a1 is 1, r is -1. So this is going to give me negative x, minus x plus x squared minus x cubed plus x to the fourth minus x to the fifth. I'll do one more. And you'll see why we need so many terms here. Now I'm going to subtract this one. So this one's a1 is 1, its r is positive x. So we're going to have 1 plus x squared plus x cubed, and so on. Okay, so if I were to subtract these, this top line minus that line, 1 minus 1 goes away. I have a -2x minus 2x is -2x. X squared minus x squared, it goes away. Minus 2x cubed, those go away. Minus 2x to the fifth, and so on. So this one's a1 is -2x. The common ratio, or multiplying to get from term to term, is x squared. So when I put this in sigma notation, I'm just going to do my a1 -2x times the common ratio x squared to the n. And again, there's other ways to simplify this, but I'm going to leave it like that. My interval of convergence is just -1 is less than x squared is less than 1, which is just between -1 and 1. All right, now we're going to create a series from an old series using integration. Okay, so if I take this derivative, this is my result. Well, the same is going to be true for this series. Okay, so I'm going to write this series out. A1 is 1, r is negative x. So we're going to have 1 minus x plus x squared minus x cubed plus x to the 4th. Okay, then I'm going to take the derivative. So this is this. So if I take the derivative of this, I get this. If I take the derivative of this, we get this in series form. So derivative of 1 is 0. So we're going to end up with minus 1 plus 2x minus 3x squared plus 4x cubed, and so on. We're not asked to write this in sigma notation, so we're just leaving it like this. But this function here can be represented by this series. Okay. Identify the open interval of convergence. So this one had an interval of convergence of -1 to 1. The open interval, and I'm going to make a note over here. When you're forming a series using differentiation of another series, it will maintain the same open interval of convergence as the original, but it may lose an endpoint, which really isn't a big deal for us right now because we don't have any endpoints to begin with, meaning -1 and 1 are not included. But when we start looking at series that aren't geometric series, the interval of convergence may include the endpoints, and when you take the derivative, you may end up losing one of those endpoints for the interval. This is something that we won't get into until Unit 9, Part 2, but I just want you to be aware of it. All right, same thing here. If I were to take the derivative of this is what I would end up with, okay? So I can write a series for this one, because A1 is 2, R is negative x cubed, so we're going to have 2 minus 2x cubed plus 2x to the 6th minus 2x to the 9th. One more. Okay, so our last one. So then I'm going to take the derivative. So derivative of 2 is 0. So we're going to have minus 6x squared plus 12x minus 18x to the 8th plus 24x to the 11th. That's my series. The interval is when that's between -1 and 1, which is when x is between -1 and 1. Okay, now we're going to integrate. Okay, the integral of this is natural log of 1 plus x. So I can develop this series with this one and then integrate. So A1 is 1. My r is going to be -t. So we're going to have the integral from 0 to x of 1 minus t plus t squared minus t cubed. Okay, and then we'll integrate. Integral of 1 is t. Integral of -t is going to be -1/2 t squared, 1/3 t cubed minus 1/4 t to the 4th, and so on, evaluated from x to 0. So we're going to plug in x, and then we plug in 0, which they're all going to go away. So x minus 1/2 x squared plus 1/3 x cubed minus 1/4 x to the 4th. That's our series. So natural log of 1 plus x can be rewritten with this series as long as -1 is less than x is less than 1. Since our integral is, or our range is -t, which would be -x and 1. There is a note on this one's, again, open interval. the note on this one, it's still going to maintain the interval of convergence of the original function, meaning in this case the 1 over 1 plus t, but if you integrate, you may gain an endpoint. So on this open interval, this one may potentially include -1 and 1. All right, tangent inverse. So tangent inverse, derivative of tangent inverse is 1 over 1 plus x squared. So we can integrate this with a1 equaling 1, r being -t squared. So we're going to integrate 1 minus t squared plus t to the 4th minus t to the 6th. That'll be t minus 2/3 t cubed plus 4/5 t to the 5th minus, 1/3, 1/5, 1/7. Don't know what I was thinking there. From 0 to x. So this is x minus 1/3 x cubed plus 1/5 x to the 5th minus 1/7 x to the 7th minus 0. So tangent inverse as a series is this expression here, as long as -1 is less than x is less than 1. So that is power series and different ways to represent them using infinite geometric series and its sum formula.